So far, we have defined curves in R3 in a mathematically precise way, and we have also discussed some of the examples, and we discussed some of the properties of these curves as well. Now, our aim is to study different geometrical properties of the curves in R3. Now, these geometrical properties should be defined in, of course, mathematically precise way so that we can use them precisely, and these properties should be such that we can differentiate any two different curves in R3. Now, one such property is known as curvature, which is the rate of turning of a curve. Now, our aim is to study the mathematical measure of turning and twist. So these two properties will be discussed in our future discussions, and what do we want to do? We want to first of all define them precisely, and secondly we want to use them, and we want to be able to calculate these things in, of course, in an efficient way. So that is kind of our aim for our further discussions. Now on the screen we can see three different curves of R3. Now the point is, of course, we can see that these are three different curves. The aim is to find some mathematical measure that can differentiate between these three different curves. Now, in the first case, you can see that the curve is turning very fast, but in the second example, you can see that it's not turning very fast, and the third example, it is a bit slower than the other two. So, and then there is also a twist in the curve as well. So there is a curvature and there is a twist. So these two quantities are the main aim for our next discussion, that we want to quantify the rate of turning, known as the curvature, and the rate of twist, which will be known as the torsion. So that's kind of the main task. Now the tools available to us are vector fields on curves, and in our first step we will define some more vector fields. So in fact we are going to define three different vector fields on any given curve, and these three vector fields are enough to classify curves. So when I say classification, it means these tools are enough to differentiate any two different curves in R3. So these are our available tools. Now there is a limit on our computations, and the limit is that we are only discussing the curves that has unit speed. So in other words, a curve beta is discussed only if its derivative and the norm of the derivative is equal to 1, which is basically the speed or the norm of the velocity. So that is our condition for simplification of the calculations. Now let's discuss what is curvature and how do we actually calculate it in a precise way. Now as we know that curvature is basically rate of turning. So we can see that the curve is now moving, and there is a turn, and then it's more or less going straight, and then once again it's turning, and up to so on. So at some points the curve is going more close to straight line, and at some points it's more close to a circle. So sometimes there is a faster rate of turning, and sometimes there is not a faster rate. So we want to be able to differentiate at what point what is the curvature of that given curve. Now let's see how do we calculate it mathematically. Okay, so given any curve beta, so we impose the condition that it should be unit speed. Okay, and if it is unit speed, then it means that at each and every point on the curve we have a unit velocity vector, because it has unit speed, so it has a velocity vector with this condition. Okay, so these are the velocity vectors at each and every point. Now what is the property of these tangent vectors? So let me call it by t. So since it is giving me a vector at each and every point, so it is basically a vector field. Okay, now if I calculate somehow the rate of change of this velocity vector, then we know that there are two important quantities about a vector. So one is the magnitude, the second is the direction. So if I'm calculating the rate of change of the vector, then it should be able to tell me what is the rate of change in the direction and what is the rate of change in the magnitude. And now, due to our condition that the magnitude is always 1, so this rate of change is not going to give me any information about the rate of change in the magnitude, because the magnitude is fixed and it is equal to 1. So what does this derivative is going to provide me then? So this derivative is going to provide me the rate of change in the direction of this tangent vector. And in other words, we will be discussing at what rate this arrowhead is changing. And by studying the rate of change of these arrowheads or rate of change in the direction of these velocity vectors, we can find out the rate of turning in the curve. So for example, at this point we can see that this arrowhead is going in this direction and there is a big difference in the direction of these arrows, and when the curve is closer to a straight line, then there is a kind of smaller change in the direction of these two vectors. So this difference is bigger and this difference is smaller in the direction. So that's why when we track, when we calculate, or when we discuss this rate of change of velocity vector, it is going to provide us basically the rate of turning in the curve, and hence we can easily calculate the curvature in the curve. Okay, so in this direction we first need to define this unit tangent vector field, because at each and every point on the curve beta we can find a velocity vector or tangent vector, and due to our condition that it is a unit speed curve, it is always going to be a unit vector, so that's why we call it unit tangent vector field on beta. So we want to now calculate the curvature using this unit tangent vector field. Now the point is, at each and every point on the curve we have this tangent vector. Okay, so I'm just writing down t for each and every tangent vector, and at each and every point I can also calculate t prime, which is the rate of turning of this tangent at that point. So this t prime is going to provide me another vector at each and every point, and this t prime may or may not be a unit vector field, because the magnitude or the length of t prime at each and every point may or may not be 1, may or may not be 1, and it depends on the curve, the properties of the curve, but one thing is sure, that we have imposed the condition that the magnitude of t is 1. And since we are getting these blue arrows, which is basically t prime, so we have another vector field which is known as the curvature vector field. Since this curvature vector field knows about the rate of turning in the tangent vectors, and hence this tangent vector curvature vector field knows the curvature of any given curve, and using this curvature vector field we can actually define the curvature function to be the magnitude of this curvature vector field. So it is basically it is going to be a function of the parameter, and at any particular point it is going to be a number which is going to tell me the rate of turning of the curve at that particular point. The curvature function, of course, it is always going to be non-negative for all parameters in the open set I, which is the domain. So if you are using t, then this is the parameter t. Now when k is small, then the curvature is too close to a straight line, and when k is large, then the turn in the curve is sharp. Okay, now of course we can guess from this example of the curve that what are the points where the curvature is smaller. So these are the points where the points are more close to straight line, so curvature is small. Okay, so over this interval curvature is small. So when I say small, it means smaller than the curvature at this point. Okay, so we have curvature value is large. Okay, now let's discuss some particular examples Of course, we only need to consider there is a condition on the curve that we should only consider unit speed curve. So we have this unit speed curve, and geometrically it represents a circle. Now, what do we know about a circle apart from its definition that it's a set of all points whose distance from a fixed point, which in this case is 0, 0, is constant. Okay, so apart from this property, so there is another important property of the circle, that the rate of turning at each and every point of the circle is constant. Now let's see if our definition of curvature is going to provide us the same information. Now, how do we calculate curvature? So we want to calculate t prime magnitude. So that's what we want to calculate. So this is the curvature. So first of all, we want to calculate what is t. So this is basically alpha prime s. It is going to be equal to minus sine s cosine s and 0. And similarly, what is going to be t prime? So alpha double prime of s, which is equal to minus cosine s and minus sine s 0. And in order to calculate the curvature, we want to calculate the magnitude of this t prime, so which is going to be equal to cosine square s plus sine square s, and we know that this is equal to 1. And we can see that this curvature function in this particular case of circle is independent of the parameter s. So whatever value of the parameter s is given, or whatever point on the circle is given, this curvature is always going to be fixed and is equal to 1. And hence it fits with our usual interpretation of the circle, that the rate of turning at each and every point of the circle is constant, and in this case this constant is equal to 1. Now let's have a look at another very typical example. So consider this line passing through point P and parallel to this unit vector V. Okay, so we are imposing this condition that V should be a unit vector, just to make sure that we are not violating this rule that our definition only works for unit speed curve. Okay, now what do we want to calculate? We want to calculate the curvature of this line. Now what do we know about line? So there is no turning in the line, and hence the curvature should be 0. Now let's see if our definition of curvature fits with our usual interpretation of the line. Okay, now we can take this point to be any particular point p1, p2, p3, and we can take this vector, unit vector, to be v1, v2, v3. But since it is unit, so the norm of v hat is going to be equal to 1. Now let's calculate alpha of s using these conditions on p and v. So this is going to be equal to p1 plus tv1, p2 plus tv2, and p3 plus tv3. Now what is alpha prime of s? So sorry, let me use the exact same parameter. So alpha prime of t. So alpha prime of t is going to be equal to p1, p2, p3. Okay, and then what is going to be alpha double prime? Since alpha prime is t and we want to calculate t prime, so this is going to be alpha double prime of t. So this is going to be equal to 0, 0, 0. And what is going to be the curvature, which is basically the magnitude of this t prime? So this is definitely going to be equal to 0. And from our definition, the curvature of this curve in R3 is 0, which once again fits with our intuitional way of imagining this straight line. Now in this discussion, we have discussed and defined curvature, which is a rate of turning in a curve in R3.